Right? So from last few lectures, we are actually talking about the few of the instructions. So I will just run through the point that we already covered. Right? So these are the instructions. Right? And we discussed about the conversion. Then we discussed about the binary arithmetic. We discussed about the MEL and IMEL. Then we discussed about division instruction. Right? In division instruction, there is an interesting point that I was talking about, and it was, see, whenever your divisor, see in the instruction or DIV instruction, it is expected that you can only specify the divisor. Divisor can be any general purpose register, right? So whenever you specify the divisor, that decides the operation size, right, or what the operand size, right, or the dividend size. Let me tell you, right, what operation it is going to carry out, right. So if I specify the operand divisor as 8-bit, then dividend will be 16-bit. So 16-bit number will be divided by 8-bit, and then the result will be available in the accumulator, or the register combinations are given, right. So whatever the dividend is there, right, the registers which are involved as a dividend, right, we can directly split it into two halves, right, upper half and lower half. In upper half you can find the remainder, and in lower half you can find the quotient, right. So always particular part. With respect to 32-bit operand, yesterday I was talking about. So EDX and (EAX) will be the dividend, right? And these are the implied operands, right? These operands we don't specify. In case of MEL instruction or multiplication instruction, we never specify the multiplicand. Like that, in case of division, we never specify the dividend, right? It is implied based on the only one operand that we specify, right? The size of divisor or size of multiplier will decide which dividend or which multiplicand will be used, right? And based on the of operation, right, the result will be stored in appropriate destination register. So this combination everyone should aware about. Now let's go for the decimal arithmetic instructions, right? Very interesting one. See, in real life we generally use the decimal numbers, right? And whenever the data is in the form of decimal, or if we want that data should be converted into decimal, right? In that case, this set of instructions are used, right? So there are basically decimal arithmetic. It is combination of it is used along with the binary arithmetic instructions. So it is mainly used to just adjust the results, right, after the calculation or before the calculation, right. So to adjust the results of previous binary arithmetic operation to produce valid packed or unpacked decimal results. Now I think you are aware about what packed by BCD and unpacked BCD. In digital electronics we discussed about it. In unpacked BCD, we used to have 8-bit number to represent single digit. So it is in the unpacked format. So ultimately upper 4 bits will be 000, and then lower 4 bits of that 8-bit will be the decimal equivalent or binary equivalent of that decimal number. So that's why we call it as unpacked BCD or unpacked decimal, right? And in case of packed number, packed BCD, we used to use 4-bit for a single digit. So in a byte size operand, we can have 2 digits, right? So if you want to represent 25 in a unpacked decimal format, right? 25 in unpacked BCD decimal format, then the result of this will be 00000010. This is the upper digit in unpacked format, and lower digit, that is 5, will be 0000, and 0101 will be the unpacked decimal format of 25. And same number, if I want to put it in packed BCD format, in that case it will be written as 0010 and 0101. All right. So now this translation, we are going to see few of the instructions, right, and it is used for that purpose, right. And the other option is to adjust the input of to a subsequent binary operation. So after binary operation or before operations, we can use these all instructions, and this is very specifically used when we are handling the BCD numbers, right? So this we need to remember. Then BCD adjustment instructions are there. So there is a DAA. So it is a decimal adjust after addition. Then second one is DAS. It is a decimal adjust after subtraction, right? Then for unpacked BCD adjustment instructions, so there is a AAA instruction is there, that is ASCII adjust after addition. Then AAS, it is ASCII adjust after subtraction. So these are after performing the operation, we can carry out these instructions. So these instructions are mainly used after the binary operations or the arithmetic operations which are carried out. So there is AAM, so ASCII adjust after multiplication. Then AAD, that is after division, right? These are the things. Now the logical instructions are there. Now there are different logical operations which are possible with the help of ALU, right? So the Boolean operation instructions are there. Then bit test and modify instructions are there. Then bit scan instructions are there. Rotate and shift instructions are there. Then byte set on condition, these instructions are there. So these are all logical instructions which are basically having operands as a binary bit. So it performs operation in binary bit. So basic Boolean operations are not, and, or, and XOR, right? So these all operations are bitwise operations. So for these operands should be minimum 8 bit. So bitwise operations are carried out. The operand will be 8 bit, 16 bit, 32 bit, right? So here only thing is whatever the operation, Boolean operation that we are going to carry out, it is a bitwise operation. So not operation, and operation, or operation, XOR operation. These operations are there. So we know how those are basically performed. So wherever we require, we generally use these instructions to perform the basic Boolean operations. Then this is one of the interesting instruction, right? Bit test and modify instruction. Now there are several instructions conditions where we need to check the condition of a bit in our operand, in the operand. So in that case, so bit test is the instruction that I was talking about, and there are several situations where we need to identify that or check the bit, individual bit within the operand. Right. Now, for example, if you want to check whether the given number is positive or negative, right? So ultimately, MSB is to be checked. All right. This is one example. Second example, if you want to check whether the given number is odd or even, in that case, LSB is to be checked, right? Without modifying the bit, or there are other options as well. We can modify that bit as well. All right. So in such examples, right, we need to use this bit test. So bit test is one of the interesting instruction that you have to remember, right? So there is a first instruction which is called a bit, BT, bit test, right? So BT itself is a bit test, right? Now, whatever the bit that we are specifying, right, in the operand as an operand, right, it will be simply put it into the carry flag. So the effect on carry flag is what? Whatever the bit that we are testing, it will be put it into carry flag. So after executing this instruction, it is our responsibility to check the condition of carry flag to decide what that bit is. All right. So here BT is having the two operand, right? The first operand will be the number. Number means it will be a register in which we want to check that particular bit, and then the comma, and then the relative offset from the least significant bit. So from the least significant bit. So if you want to check the lower LSB, then in that case it will be 0. And if my number or register that I'm using is a 16 bit, in that case, if I want to check the MSB, then the bit that I need to specify as a second operand will be 15. So we know the numbers are 0 to 15, right? Whatever the bit numbering that we are giving to the number, for 16-bit number. In that case, it will be starting from LSB as 0, then 1, 2, 3, like that up to 15. So depending on the want to test, right, we have to select the second operand as a bit number, right? And whatever the test, it will be carry flag. Right. Now, after execution of this instruction, it is our responsibility to check the condition of carry flag. So there are several conditional instructions which we will see later on, right? But here, along with the BT instruction, it is mandatory to use the conditional jump instruction, right? And that is again checking the condition of carry flag, because that is the only flag which is getting modified to read or to specify the current status of that particular bit. Right. So now, for example, if you want to check whether the number is positive or negative, in that case, what you will do? You will simply write this BT instruction to check the positive or negative number. So MSB will be there. So you will write the register comma and then 15 you will write, and then you will check jump if carry or jump if no carry condition. You will use any of these, and then based on the condition, it will jump to the location where you can increase the count of particular numbers, right? So whether it is if it is positive number, then we'll increase the positive count. If number is negative, then we'll increase the negative count. So we in lab we will discuss about how it is exactly used, right? So here the next instruction is BTS, right? Bit test and set. So there is a difference between these two instructions, right? Before actually, this is the first instruction is BT, which is very simple, right? Straightforward. The bit that we are testing, it will be moved to the, it will be stored into the carry flag. Now here in this case, what is the condition? It is basically it is additional operation that will be carried out after checking that bit. So it is a bit test and set. So whatever the condition of that bit is there, it will be modified to 1. So effect on selected bit is specified. Effect on selected bit, right? So ultimately, it is going to modify that particular bit as 1. But before that, it moves into carry flag. Then BTR, so bit test and reset. Bit test and reset is, it is going to test that particular bit and it will reset. Reset means it will make it 0. And then the fourth one is BTC, bit test and complement, right? With bit test and complement, it is going to complement that particular bit after putting it into carry flag. That is a operation, additional operation that will be carried out. Now there is a bit scan, right? There is a bit scan which you can see here. Bit scan instruction, we can scan the bit within that particular operand, right? So here, scan a word or double word for 1 bit and store the index in the first set bit into the register. So this is interesting one. See, whenever we want to check at which bit position there is a first bit, right? There is a first bit. So we have 2 options, right? From the LSB side or from the MSB side, we can scan the bits. So here bit scanning will be done in forward direction, and bit scan can be done from the reverse side. So here you can start it from LSB and you can start it from the MSB as well. And wherever your pointer stops, right? Wherever your processor gets the first bit, then that index will be simply stored in the register, right? So the alternate second register will be having that particular index after execution of this instruction, right? So ZF is set if entire operand is 0. So ultimately, outcome will be in either index in the register, second register, or ZF will be set if operand is 0. So if there is no 1 in that operand, then ultimately index will be treated as invalid 1, and ZF will be checked, right? If ZF is 0, that indicates the operand is 0. Right, in which we are scanning the bit 1, right? Then shift and rotate instructions are there. These instructions are an interesting one, right? Shift and rotate. Now there are several operations, right? So if you have a notebook, you can simply write this particular part, right? Very interesting words that I'm going to tell you, right? Now, if you use this shift and shift instruction or the rotate instruction, right? There are as we are working on a binary number, right? So if you simply take one single number, right? So say 3 as a first number, right? So if you write it in binary 0, 0, 0, 0, 0, 0, 1, 1, 8-bit number that I'm telling you, right? So if you write it 0, 0, 0, 0, right? So in chat box I will simply put that number, right? 03. So it is 0, 0, 0, 0, 0, 0, 0, 1, 1. So it is 3, right? Now if I am shifting it towards left, right, shifting towards left. So ultimately, what is going to happen? This MSB will be taken out, right? So it will be moved into carry flag, right? It will be moved into carry flag. And in case of shift operation, 0 will be inserted from the LSB side. So from the right side, as we are moving, shifting it towards left, so 0 will be inserted. And as a result, you can have this carry flag equals to 0, and the number in register will be 0, 0, 0, 0, then 0, 1, 1, 0. All right. All right. So this CF will be 0 because the MSB was 0. So that is shifted into carry flag, this MSB. And then these lower 4 bits, you can see here, upper 4 bits here. Then 0, 1, 1 with inserted 0, you can see it as a lower 4 bits. Now, if you see the number, right, this magnitude, you can see the first number was 03, right? First number was 03, and second number is 06. So here you can see easily relate, right? What is the relation between these two numbers? It is multiply by 2. It is multiply by 2, right? So you can take any number, right? So whenever you shift a number towards left side, then you will see that it is simply multiply by 2. Getting it? So you can take any example, right? So you can use 2, and if you rotate it 0, 0, 0, 0, 0, 0, 1, 0, and if you shift it towards left, then it will become 0, 0, 0, 0, 0, 1, 0, 0. So which is 4, right? So ultimately 2 and 4. So whenever basic division, right? If you want to simply divide the particular number by 2, right? You can simply shift it towards left, right? On the right side, if you are rotating the number or shift, mainly it is shift operation. So if you are shifting towards the right side, what will happen? Right. So it is a divide by 2. So there are few examples where we will need this particular instruction where we want to divide and multiply by 2. Right. So you can just make note of it. Right. With the shift and rotate instruction, there are interesting points. Right. With the shift operation, there are two types: arithmetic shift and logical shift. So arithmetic shift and logical shift. Now, in case of arithmetic shift, it is expected that it should preserve the sign bit, and in logical shift, the MSB will not be preserved. The sign bit will not be preserved in logical shift. So wherever you are handling the sign numbers, then in that case, it is expected that you should perform the arithmetic shift. So here, whenever you are shifting the number towards the right, right, arithmetic shift right and logical shift right, in both the cases, right, in the logical shift right, I told you that simply from the left side 0 will be inserted. Getting this? But in case of arithmetic shift right, whatever the MSB is there, it will be repeated to the same location. Whatever MSB is there, it will be repeated to the same location. And if you talk about the left shift operation, in that case, both will be producing same result. So there is no difference between the results that we are getting here. Right. So in case of arithmetic shift left and arithmetic logical shift left, right, the results are same. So only benefits that we are going to get with the arithmetic right, or where the sign bit is preserved, is the right shift operation. Getting this? Here, I will give you one example, right? Say I have a number 1100, then 0010. This is the number which I am shifting towards right side, and that is a logical shift, right? So for logical right shift, only 0 is getting entered into the left side, right? From the MSB side, 0 will be inserted. So here ultimately the output will be this 0 inserted, then 1 1 0, the next one is 0 0 0 1, and carry flag will be 0, right? The 0 which is going out from the LSB as we are shifting towards right. Right, so this will be the logical action. But what about the arithmetic? In arithmetic right shift, in this case, there is a very special thing that is happening, and that is the whatever the sign bit is there. Now, out of this number, my sign bit is 1, so it will be repeated to the same location. So it means that it will not really insert the 0, right? Whatever the sign bit is there, it will be repeated. So it will kept 1 as it is, right? And whatever the shifted bit is there, so next 2 bits are 1 1, because in my operand there is a upper 2 bits are 1 1. The next 2 zeros are there. So here MSB is repeated to the same location, then 1 1 0, right? Then 0 0 0 1, and your carry flag will be 0, because the 0 that is going out. So here this is the operand that I am talking about. All right. So then this is the basic difference between your arithmetic shift and logical shift. All right. Then we have double shift instruction, SHLD and SHRD, where the double operands are basically used. In this case, the single operand is used. Then rotate instructions are there. So shift and rotate instructions are basically closely related, but only difference is it is rotating the bit that is going out. In case of shift, I told you, this bit is not rotated anywhere, right? If we are shifting it towards right, then earlier carry flag will be lost. So ultimately, whatever the earlier carry flag is there, we will not be able to retrieve back. But when we are talking about the rotate instruction, then we have options, right? Rotate left without carry, rotate right without carry. So ultimately, carry is not getting rotated. But other set of instructions are there, RCL and RCR. In these, carry is also rotated, right? So in this, carry is also rotated. So ultimately, you can see carry bit can be preserved in that case. When you see where there are various operations where you want to keep that carry in the operand itself. So in that case, you can use through carry, right? So RCR or RCL, these two instructions are there. Right. So whatever with the rotate or shift operation, whatever the bit which is going out, remember this, it will be by default moved to the carry flag. By default, it will be moved to the carry flag, whatever the bit which is going out. So when you are talking about the rotating or shifting right, then LSB is going out. And when you are talking about towards left, then MSB is going out. So by default, it will be moved to the carry flag. But in case of shift operation, a real flag will be overwritten. In case of only rotate instruction, right, without carry, in that case, the bit that is going out, that is rotated in the other end. That is also rotated in the other end. So in addition to the carry flag, the bit which is going out, it is again rotated into the other end. Right. So if you are performing rotate right, in that case, the bit which is LSB which is going out, it will be moved or rotated to the MSB position. Right. It is not like the shift operation. So if I take the same example, say this is the number. Right. Or we'll take this example. Right. This example. So in this case, if you are performing rotate right, right, for this, say ROR instruction that I will use, right? So this ROR without carry, this ROR is without carry. So in this case, the output of this operation will be, now as it is rotate right, so this 0 is going out. So what I told you, this 0 is also moved into carry flag, but this is also moved to the MSB. So ultimately this 0 you can see, right, which was LSB here, right, and then 1 1, then 0, then 0 0 0 1, this will be the result, and then carry flag will be equals to 0. This is how this operation is going to carry out. when we are talking about the rotate right. And if you are performing the rotate left, same operand, 1100 this operand. So in that case, for the same operation, as we are performing left operation, so one is going out, so which is also rotated in the other end. So ultimately, this will be 1000. Then it is 0101, and the bit which is going out is also put it into carry flag. So carry flag will be 1. Right. So in this case, the bit which is moving out is right, as it is we are rotating it towards the left. So this is a very interesting set of these. All instructions are very interesting one, right? Then byte set on condition. These are basically the condition instructions, right? We can set a byte or to 0 or 1 depending on any of the 16-bit conditions defined by the status flag. So depending on the conditions, right, either we can make particular operand, like the byte as completely 0, or we can make it all bits 1. So there is a SET set instruction, and then CC is there, that is a condition code. So we can use any of the flag bit or status flag bit, and then that status flag bit will decide if it is that flag bit is 0, then it will make that particular operand as 0. If it is 1, that flag bit is 1, then it will make that register content as 1. The next instruction is test instruction. This test instruction is very interesting one, right? This is equivalent to the logical AND operation. Only difference is it is like a compare instruction, right? What I told you about the compare instruction actually performs arithmetic operation subtraction, right? It is performing subtraction operation. But only difference is it won't store the result in any of the operation. Same thing happens with the test instruction. It performs the logical AND operation, but result is not stored anywhere. Only thing is flags are getting modified. Alright, so this is very interesting. In one of the assignment, we'll be using this test instruction, right? Then control transfer instructions are there. I think it is 1 o'clock. I think we started little late, so I will extend. Our timing is up to 1:05, right? So I will continue for next 10 minutes so that. All right. See, these are the control transfer instructions. Now, very interesting set of instructions, and all of you should aware about all these instructions, because they see you are writing for loop, you are writing if loop, right? You are writing different loops, right? You are checking different conditions with the different high level syntax. Now, how it is actually checked, or which instruction is associated to that. So let me tell you that these control transfer instructions are basically associated to all those conditions, right, which we are all those loops. All right, so you can take the example of if loop or for loop, right? For all those, you need the instructions which are also checking the conditions, right? So there are two types, right? The control transfer. The first one is unconditional transfer instruction. Unconditional transfer instructions are not going to check any condition, right? Whenever this instruction is there in your program, branch will be taken, right? Branch will be taken. Now, whenever we are working with the control transfer instruction, we should aware about branch will be taken or not. That will be that we need to understand. So in case of unconditional transfer instructions, branch will be always taken, because we are not going to decide this execution of this instruction based on any condition. That's why it is unconditional transfer, right? So we have near and far jump, near and far instructions. Now what that near is and what that far is, right? Now when we discussed about the segmentation, right, segment part, in one of the discussion, I told you that we can have around 16K segments. Right? In one of our discussion, we can have 16K segments. Now, if you are jumping within the same segment, then it is known as near jump. It is known as near jump. So all of you make note of it, right? Why it is called as near jump? Because we are, whatever the target address is there, right? The target address or the branch address, it is there within the same segment. It is there within the same segment. But if you are transferring control, or if you are jumping from one segment to the other segment, right, the branch address or the target address is in other segment, in that case we have to call it as a far jump or far transfer, right? So far, it is a far location, right, which is outside the current segment, right? So here there are 4 instructions: jump, JMP. So it is a one-way transfer of execution. So we can move from one point to the other point directly using JMP instruction. So here in this case, no return is expected, right? Only one side transfer is there. Call instruction is there. Call is calling a procedure. So whenever we want to call a procedure, right? So in modular programs, we used to write or divide in our task in different modules, and we used to write procedures for it. And those procedures can be called within the main body or main program by using this call instructions, right? So many times in high level language, we used to call it as a function, right? Then user defined functions are there, which we have to define somewhere in our program. But in main body, we used to call it, right, by specifying the function name itself, right? So same thing happens with this, right? But the instruction is used for that operation is called. So there are several options of passing the parameters. So in detail we will discuss when we actually use it, right? So call is that calling used for calling a procedure. And if you this is basically bidirectional transfer. So bidirectional means what? We are going to that particular location, branch address, and then from branch address we have to return back to the address from where we are jumping. We are transferring control to the procedure, right? So for that we use RET instruction. So RET is very specifically used for procedures, normal procedures. So call and RET are associated to each other, right? So whenever you write a procedure, then the last instruction which will be executed from that particular procedure will be RET, right? And RET, what is the role of RET? It is expected that it should return to the location from where we called the procedure, right? Now in detail, when you explore the addresses, return addresses, right? Many times in high level language also we are using the functions, right? So whenever you are calling a function, return address is stored onto the stack. That is very important part, right? Return address is stored onto the stack. And whenever you are executing RET instruction, then this return address from the stack will be popped out, and it will be stored as a return address for that particular procedure. So here from that procedure, we can return back to the location, right, after this call instruction, right? So here, next version of return instruction is IRET. Now, IRET is the instruction which is associated to interrupt service routines or interrupt service procedures. Interrupt service procedures are the specialized codes which are basically written to provide the service, right, different interrupt services. So how it is used? So for example, if I give you one example, right? So let's take one example of industrial safety solution. And in that, if we have a fire sensor, right, installed at a hazardous location, right? So if there is a fire sensor, then what will happen? Then if we have installed sprinkler over there for as a fire extinguisher, right? So in that case, it is expected that it should start the sprinklers at that locations. So whenever there is a signal from that particular sensor, then your system is going to execute the code associated to starting the sprinkler at that particular location. So this is, we can treat it as an interrupt service routine. So whenever particular interrupt is received, then your code will stop its normal function, right? And then it will execute that particular code which is associated to that particular interrupt. So providing the interrupt. So there are in computer hardware, right, there are several interrupts, right? Whenever you plug in and plug out the devices, you used to always, your operating system is, whenever you plug in new device, it is getting interrupted, right? So there is a new device detected in your system, and then it will ask you to, well, do you want to install the software or the device driver for that, or if it is plug and play, then it will ask, it will start initialization, right? So that then that kind of interrupt service routines are basically there available in your systems. Then we have keyboard interrupt, we have mouse interrupt, so many things. Whatever the devices we connect to the system, right, many devices are handled as an interrupts. Then the conditional transfer instructions are there. This set of instruction is very interesting, and very frequently we will be using it. So all of you make note of it. Conditional transfer instructions. There is a very important point that I need to highlight here. Right, there are two categories of these conditional jump instruction. One is used for unsigned conditional transfer, and other one is used for sign. So on the next slide, it is written signed conditional transfer instruction. So here, these are the signed conditional transfer instruction, and these are the unsigned conditional transfer instruction. What is the difference here? Here, see, as I told you, if you are comparing two numbers, right, in compare instruction, if you are comparing two numbers, and if those are unsigned numbers, in that case, to check any of the condition, you have to use any of these instruction here. So for example, if you want to check whether the numbers are equal, or whether the number is I can say above or below, right? Right, I want to check whether the number is above or below, right? And my numbers are unsigned numbers, right? So in that case, I have to use a JA instruction. JA indicates what? Jump if above. Jump if above. So jump if above will treat those two operands as a unsigned operands. But if my two operands are signed numbers, in that case, I have to use JG instruction. It is a jump if greater. So above and greater both are so differently related, right? So greater is a term that is used in case of signed numbers, and above is a term that is used in case of unsigned numbers. Now, if you are comparing, right? So if I give you an example in chat box, I will simply put that particular number. So first number is say 05 is my first number, and second number is 85. Right now, if you just focus on these two numbers, and if I ask you which is bigger number, so answer will be 85. Right, which is bigger number? So 85 will be the answer, right? Now, if I change the statement, right, these two numbers are signed numbers. If I tell you that these two numbers are signed numbers, in that case, which is the bigger one? 05 will be bigger one. How? Because 05 is a positive number and 85 is a negative number. Right? How 85 is negative number? So if I put it in binary, 85, so it will be one of the, see, both numbers are hex numbers, right? So that is another condition that everyone should have, right? So this is 85 representation. Both numbers are hex numbers, right? So in this case, you can say this 85 is a negative number, right? So as negative number is there, so just it is towards the left side of 0. So ultimately, 85 will be lesser than the 05. So ultimately, you can see these conditional instructions, right? Jump if above or equal, jump if below or equal, jump if carry, jump if equal, jump if not carry, jump if not equal, jump if no parity, jump if parity. These are the instructions which we will be using with the unsigned numbers, right? And then JG, jump if, that is jump if greater, JGE, JL, JLE, jump if less or equal. Now here the greater and less, these two terms are changed. In unsigned conditions, it is above and below, right? It is above and below. But in this case, it is greater or lower, less, right? Then there are instructions, right? Overflow, which are going to test the overflow of flag. So JNO is there, so that is jump if not overflow. JNS is there, so jump if not sign. Then GO is there, jump if overflow, and jump if no sign. So these are the instructions, right? So there are associated flag bits, right? The conditions which are getting tested. So you can simply refer to this particular table to explore more about it. And when we use these instructions, then it will be more clear, right, in programming. So at this stage, you can just make note of these instructions and their explanation. Right? So here there are alternate instructions associated to JG, and that is jump if not less or equal. So alternately, in place of JG, I can use JNLE. Both are having same opcode, because both are having going to check the same set of flag bits and going to check the same conditions. So not less or equal means we are checking the greater conditions. All right. Then loop instructions are there. So this is the last set of instruction that we will discuss. I think we should stop here.